In the last video I showed an LED source follower type detector, and in that video you could see a lot of noise coming from various environmental sources, mostly 60 Hertz noise, either electrically being picked up or optically being coupled into the LED through room lighting. So anyway, if you use a boxcar integrator, it's possible to get rid of some of these noise sources and not be sensitive to them. So especially when you have a weak signal or a low responsivity detector like an LED type photodetector in a noisy environment, the output to signal noise ratio can be very poor. So in that case you can use a boxcar integrator to actually look at the signal of interest and reject any extraneous signals. The other thing is the boxcar integrator can look at specific points on the integration waveform or the actual waveform, whether it's be integrating or not, and reject noise at that location. If it's uncorrelated, it becomes essentially insensitive to it and only will detect the signal that is synchronous to the trigger signal itself. The other thing we can do, and I'm not going to go into this in this video, is we can reconstruct the entire waveform, in this case the integration waveform, by sweeping from one end to the other within that trigger window, and with that you can actually plot that and noise free essentially. The slower you do it, the more averaging, the more noise rejection you get. So this is going to be a fairly short video. I'm not going to go into the details of the LED based photodetector, and I'll put a link to the description below of the video I did earlier. This time I'll just focus on how I connected the source follower output to the boxcar integrator and how I set up the trigger and so on. And we'll look at some of the waveforms on a single LED, and a red LED in this particular example, and just play around with some of the features that we can use and go from there. Hi again. This time I'm going to use the boxcar integrator to look at the output of the source follower detector, which I used last time to measure the sensitivity of an LED. So in this case, what I'm going to do is put a voltage divider at the output of the source follower, and that's a 5K and a 510 ohm resistor network divider, which basically reduce the amplitude by about 90% or so. You can actually calculate the reduction in voltage here, and so that it doesn't exceed the 2 volt swing that this signal input can handle on the boxcar. So the only thing I need to do is to add the trigger, which I applied as reset over here to the source follower, into the trigger input of the boxcar integrator, and I'm going to look at the average out signal, which is going into either to digital input or some other input like the bar graph input or the analog input. So the two things I can play with here on the boxcar integrator are the delay, where I want to sample the position of the decaying signal that was coming out of the source follower detector, as well as the width of the integration. So the narrower it is, the shorter the period it's going to measure, and the delay you want to try and measure in order to get the full the swing of the LED. Before it resets, you want to basically take the delay right to the edge of the reset where the reset occurs. So that will give you the maximum amplitude change as far as the leakage or the current that is detected, the photon current of the LED. So let's look at next this experiment and see how the boxcar integrator helps to actually do a quantitative type of measurement on this with this LED and the source follower setup. So here I have the setup going for the boxcar integrator measurement, and as I described on the board, it's going to be fixed. I'm not going to use a scanning function of the boxcar. I'm going to use the fixed, the built-in scanner, which is part of the 250 SRS 250 module. I'm not using the extended scanner, which has more features, but for this particular experiment this will do. So I have the same board down there, which shows the PC board with the transistors that I used to reset and to also do the source follower to be able to measure the output The LED is this time a red LED, which is kind of medium sensitivity LED as we saw from the last video. And right now there's no light here, but I'm actually using flickering source, which is actually derived off a LED lamp, so it's going to have some noise on the frequency related noise on the light itself. And right now with the light off, you can see there is considerable amount of 60 Hertz or something in the neighborhood of 60 Hertz, I believe, ripple going on, which is just coming from the ambient light right now. So the idea of this experiment is to show that the boxcar integrator can reject any noise that is uncorrelated with this trigger. In this case, I put the trigger at 8.8 milliseconds, which is totally unrelated to the 60 Hertz mains frequency noise that may be either electrical or optically being coupled into the LED. So we'll take a look at where I'm positioning the trigger. As you can see right now, it's hard to see on this scale, but you can see it's actually right before the reset occurs on this particular display here. So back to the zoomed out view, you can see how much variation there is on every cycle of this trigger that's going on. And so you can see that the boxcar integrator is an extremely useful tool to measure these kind of repetitive type of signals which are corrupted by environmental noise on the actual signal you want to measure. So right now I'm sampling right after the reset, so it's going to measure the peak value, and you can see that on the boxcar I have 7.86 units, 7.85 units of or probably volts, if you probably close to that in actual measurement terms. So right now there is very little averaging going on, average of 3 or so, and the delay is such that I can actually move it back and forth on around this point where if I move it to the left of the reset, it's going to measure the full amplitude of the change in the voltage across the capacitor due to the discharge of the by the photonic current of the LED. So I'm going to now turn on this light, and you can see that it will immediately, the voltage will have a significant change now. And now this is the actual slope you can see coming off the discharge of the capacitor, and still corrupted by the environmental noise pickup of 60 Hertz kind of noise here. The frequency is coming off the trigger is around 120 or 130 Hertz or so, which is away from the 60 Hertz, 120 Hertz, and those kind of harmonics of 60 Hertz. So let's zoom in over here and show you where exactly I'm sampling. So it's just past the reset. The reset edge is right here, and the width of the reset is, you can see, it's about little over a division, which is going to be 20 microseconds per division, so about around 25 microseconds of reset time, fairly short. But the sampling window itself for this boxcar is even shorter, narrower. It's about a microsecond or so, I think, 1.5 maybe. Yeah, so it's about 2 microseconds in this case, so it's still very narrow. Now the voltage here is 7.82. If I move the sampling point just before the reset comes on, as you can see, it's got a lot of variation because of the 60 Hertz interference, but this voltage is reasonably stable. And if I move it further away into the you'll see it becomes a little bit better. Anyhow, it's order of, without any averaging, it's going to look a little bit noisy, but I can improve the stability of the signal by filtering out even more by averaging. So with the averaging turned on to about 10 samples, I'm seeing only about a fairly clean 6.12 volts or 6.14 units from the boxcar. The other thing we can do is to change the width of the sampling. That is this yellow pulse, the sampling window, and that's done by this knob here. You can see I widened it, so that's adjustable, as you can see, and the closer I get to the reset point, the noisier likely to hit the reset, and it's going to get noisier. and of course move it away, it will definitely help also. The other thing I want to do is to show you the bar graph, which is another function here. So if you look at the meter here, I'm going to go to the bar graph display, and of course there's no digital value here, but that's the bar graph, and you can see it's fairly stable. It's got a peak level and there's an average level, which is the two points here, and there's some noise on top of that, and you just change the averaging, that will clean it up. So if I remove the averaging, you can see it's got a lot of the LED is blinking rapidly, indicating that it's going through these different points as it measures different samples. Going back to the longer averaging, another thing we can do is to move the points around and see what happens at this edge, and you can see the peak and the average value is shifted quite a bit now, much more variation. So that brings us to the end of this video. I hope it was informative. Wanted to do it quickly and didn't want to spend too much time rehashing the same stuff. So hopefully this was useful, and how to use a boxcar integrator in an application such as this one. Thank you.